Hey everybody. Sorry that I can't be here today on Monday. Had to take care of some things at home, but so we didn't miss a day, I wanted to give you a class recording that is basically like me running class, and so we don't lose a day and we can kind of go through some examples and make sure that we're keeping up on the things we're supposed to do. So up on the calendar, we'll start off, and first thing on the calendar for today, the description of today's class is called Free Body Diagrams and Newton 2. So Newton's second law, but also analyzing it now a little bit more complex. Over the past week, we've introduced Newton's first law and Newton's second, or I'll save that for later. Tomorrow, when I'm back, we will talk about gravity, weight, normal force, and apparent weight, another application of Newton's second law. Wednesday, I'm actually going to be gone in the morning, so I'll have an activity for you guys there. So if you're first period or second period, you're going to actually not have me twice this week, which, depending on how you look at it, may be good, may be bad, I don't know, whatever. Then on Thursday, we'll get into equilibrium, and you'll see that equilibrium will actually take us through Friday, but then also Monday as well. So that's where we're headed for the next couple of days. I wanted to start off today. First, if you haven't gotten a copy of the sheet for today, it looks like this. It's on the back tray, 5.2, Applying Newton's Laws, and the first part is called Diagramming Forces. So, reviewing briefly what we've done so far. Section 5.1 was about Newton's laws of motion, and we spent a lot of time analyzing and looking at examples of Newton's first law and Newton's second law. So Newton's first law, inertia, things staying the same, things continuing to do what they are currently doing unless a net force acts on them. Then we went to Newton's second law. We said that if Newton's first law deals with things remaining the same, Newton's second law deals with acceleration, deals with things changing. And we talked about that the idea is that acceleration is determined by two factors, force and mass, but then we also talked about the idea that it's not just force we have to be concerned with, it's also net force, the vector sum of the forces. And we're going to get into that a little bit more today. And then on Friday, we finished up this first section of Chapter 5 looking at, where is it? There it is. Looking at Newton's third law. And we said that Newton's third law deals with action-reaction, that forces come in pairs, that we can't ever have a force in isolation, that there's always two forces. And those forces are equal in magnitude but opposite in direction. But we also talked about the idea that they act on different objects, therefore they do not result in net force zero, and we can still have things moving even though we are describing forces as equal and opposite. So today, I wanted us to get started on this section, 5.2, Applying Newton's Laws. Over the next week and a half, we're going to do several example problems where we are going to use the concepts that we talked about in Newton's first law, Newton's second law, and Newton's third law, and apply them to physical situations. See how these concepts of inertia, acceleration, net force, and action-reaction go into explaining physical things that we see in the real world. So the first part that we need to talk about before we do that is the top of your sheet, and it says diagramming forces, and more importantly, free body diagrams are useful in applying Newton's laws. So first, free body diagram. I'll go back to the book for a second here. Free body diagram and you guys probably won't be able to see this, but the free body diagram is defined as a sketch that shows all the forces acting on an object. A sketch that shows all the forces acting on an object. So, we've talked about the idea that net force is the vector sum. If we're going to find the vector sum, we need to examine all of the vector forces, or the force vectors, that are acting on an object if we're going to find the vector sum or the resultant vector. It's a sketch. Different people draw different different people draw free body diagrams different ways. There is no right or wrong way. I think there is a way that is effective in terms of seeing how the forces interact with one another in order to produce the resultant force. But if you draw a picture and it helps you analyze what's going on, I'm perfectly fine with that. So, our first order of business today is going to be analyzing and constructing our own free body diagrams. Down at the bottom, the key point to this first part of section 5.2 says, once all of the forces are drawn on a free body diagram, a coordinate system is chosen, with each force resolved into components. Once all of the forces are drawn on a free body diagram, a coordinate system is chosen, and each force is resolved into components. At this point, Newton's second law can be applied to each coordinate direction separately. Now, the book and I are going to deviate a little bit here at this point. I don't agree exactly with how the book does this. I think they've made it a little bit harder than it needs to be, at least at the beginning. But this idea that Newton's second law can be applied to each coordinate direction separately is going to be an important one when we start analyzing a little bit more weight, normal force, apparent weight, and then especially when we get into equilibrium later this week. So, we introduced the idea of Newton's second law earlier last week, and we said that Newton's second law is summarized with that equation, right? Sigma F is equal to m times a, where sigma F represents the net force, the vector sum. What that key point is telling you is that when we go in multiple dimensions, we can analyze the net force only on the x-axis if we need to. And we can also analyze the net force only on the y-axis, like we talked about in the last chapter with projectile motion. Even though there may be two things happening simultaneously, they are independent of each other. Yes, they may both influence the motion or the ultimate outcome of the situation, but they are independent of one another. And we sometimes can analyze them independently of one another, and we'll talk about that when the time arises. So, a free body diagram, a sketch that shows all of the relevant forces. Okay? And we'll talk about those free body diagrams here in just a second. So, at the bottom of the page I gave you today, you have a situation that shows two astronauts working on a satellite. So it says, consider a situation where two astronauts are using jetpacks to push a 940 kilogram satellite towards a space station. If each astronaut pushes with a force of 46 newtons, what are the magnitude and the direction of the satellite's acceleration? So this problem, like now we're getting back into solving problems, so we should be consistent with our format, consistent with our procedure. When it says What are the magnitude and the direction of the satellite's acceleration? It's asking us for A. Now, in this case, we have to think about the influence of both of them. So whereas here, in the last page, we talked about there being a separate acceleration on the x-axis and a separate acceleration on the y-axis, in this problem, they don't want either of those specifically or independently. They want the overall acceleration. So, a couple more things that we need to know here. First, if it says that it's a 940 kilogram satellite, right? The fact that it's in kilograms gives us the mass. And then it says there are 2 astronauts using jetpacks to push a 940 kilogram satellite towards a space station. It says if each astronaut pushes with a force of 46 newtons, what are the magnitude and the acceleration of magnitude and direction of the acceleration? So here we have 2 forces. One coming from astronaut number 1, and 2 coming from astronaut 2. Now, here's where the free body diagram really becomes important, because we know from the previous section that forces are vector quantities. They need to tell us both magnitude and direction. But in the way that this picture is, we can't really just call one positive and one negative. Even though they're in different directions, they're not completely opposite of one another. So again, we end up with a situation like we did in chapter 4, where we have a coordinate system that's going to have to take care of both horizontal things and vertical things. Over here on the right, there's a picture of these 2 astronauts, and part B is labeled the free body diagram. It has both of those forces shown up, or showing, and how they are acting on the satellites. Now, so that I can do what I need to do with them, I'm going to write over them using my different colors. Okay. So this right here, actually, do that a little bit. That right there will represent force 1, and this right here will represent force 2, just like in your picture, but now I got them color-coded, and that'll be important a little bit later. Okay? So, first, free body diagram. While I said that there's different ways to write free body diagrams and different ways that we can do them, as long as they help you analyze the problem, that's okay. However, most free body diagrams you will see start with all of the forces beginning at the same point. And usually, if we're talking about like this satellite here, we'll pick a point just right in the middle. And we'll draw all the forces coming out of that point to represent that they are acting on the middle, and then that shows us the direction. Again, because forces are vectors, we can use arrows to represent those vector quantities, just like we have in this picture. Okay? Now, we learned back in the first part of this section, or of this chapter, chapter 5, that the acceleration of an object, hold on a second, that the acceleration of an object is dependent upon 2 things: the net force acting on that object and the mass of that object. Now, sigma F, right, the net force we said was the vector sum. So in this case, we would modify this equation to look like this: F1 plus F2 is equal to m times a. Now, so that we don't get confused, right? That net force is a vector sum. I have it just written as F1 plus F2. But if we add, right, our little vector notation, now we're not just adding the magnitudes of F1 and F2, we're adding the vectors F1 and F2. So before we continue on with this, let's go back to our free body diagram. First, to find the vector sum of two vectors, they need to be arranged properly. That proper arrangement requires that they are set up head to tail. In this free body diagram, those vectors are not set up properly in order for us to find the resultant vector. Now there's two ways we can do this, right? Because I have it written as F1, vector F1 plus vector F2, I'm going to take blue and I'm going to move it to the end of red. Not that I need to do this. Oh, whatever. You'll get the point. And then we said that the resultant vector is drawn from the beginning of the first to the end of the last. Just like that, right? Same thing we did back in chapter 4, finding the resultant displacement or finding the resultant velocity. Now we're using forces. That pink vector drawn on this picture is the vector sum of force 1 and force 2. And we learned back in the first part of this chapter that that represents sigma f, or we use sigma f to represent the vector sum. Here, right, we know that F1 is 46 newtons, and we know that F2 is also 46 newtons, but the resultant here isn't going to be 46 plus 46, 92. That's not going to be the case, right? In order to find that resultant, we have to use Pythagorean theorem to find the hypotenuse of that triangle. So go ahead and do that now. When I do it on my calculator, I get that that hypotenuse is 65 newtons. We're going to need a direction here. Well, let's hold on to that just for a second, okay? So, going back to this arrangement, applying Newton's second law to this situation where we have two forces acting on an object, although they're not in the same direction, they're at right angles to one another, we just calculated that the resultant vector of these two force vectors is 65 newtons. We already know that the mass of that satellite, 940 kilograms, so we can plug that in, and we're looking for the acceleration. Now we can just solve this equation for A. So we take 65, we divide it by 940, and we end up with the acceleration is equal to 0.069 meters per second squared. Okay? That doesn't fully answer the question, though, because this is just the magnitude of the acceleration. The question specifically asked us for the magnitude and direction. Well, net force causes acceleration. So, hopefully it makes sense to you that the acceleration is going to occur in the same direction that the net force is being applied. In our free body diagram, that would be in this direction represented by the purple arrow. If you remember anything from geometry, hopefully you do, this triangle is a specific kind of triangle. When the two sides of a right triangle are the same, right? That means if this is a right triangle, that angle has to be 45 degrees. So does the other angle at the top, but that angle specifically, because it starts at our origin of our coordinate system, right? That spot being the middle of the object, we'll call that the origin of our coordinate system. Okay? So, when we go here, the net force is actually 65 newtons at 45 degrees above the positive x-axis. But because net force causes acceleration, the acceleration will as well be 45 degrees above the positive x-axis. Just like we did in chapter 4. If it asks us for a vector quantity, we have to give both magnitude and direction. The number is the magnitude. It's not positive or negative because it's not on an individual axis. This takes care of the direction. So we're taking those concepts of net force and how it affects acceleration and just applying it to two dimensions. If you flip to the back of the sheet that I gave you today, active example 5.6 says, suppose the force exerted by astronaut 1 is increased to 58 newtons. If everything else in the system remains the same, what are the magnitude and the direction of the satellite's acceleration? I'll walk you through this one again. So, what are the magnitude and the direction of the satellite's acceleration? That means we're looking for acceleration. It says that the force exerted by astronaut 1 is increased to 58 newtons. So F1 is now 58 newtons. But it says if everything else in the system remains the same. So the mass is still going to be 940. And F2 is going to remain 46 newtons. Before we start analyzing this situation, we should draw ourselves a free body diagram. First, this is astronaut 1, so he's going to push in this direction. There is F1, and we just learned that that was 58 newtons. This is F2 in the free body diagram. Remember, a lot of times it's beneficial to draw our forces originating from the origin or the center of the object and pointing outward. So in this case, it's probably going to be beneficial to help us analyze this problem if we go like this. Now, remember, 58 newtons for force 1, 46 newtons for force 2. If we're drawing arrows to represent those two forces, we should draw the red longer than the blue to represent the greater magnitude. All right. Just like we did before. If we want to find the acceleration of an object, we have to consider both the mass and the net force. The net force is still defined as the vector sum of F1 plus F2. But we should use that vector notation so we distinguish between just adding the magnitudes together or finding the resultant vector. On the other side, we still know the mass, and then that combines to give us the acceleration. Again, we're looking for sort of the resultant acceleration. So, to find the net force of two vector, or find the net force, we have to find the resultant vector of two vector quantities. Over here, those arrows are not aligned properly to find the resultant vector. I'm going to take blue, move it over here. So it starts where F1 ends. Then, resultant vector from the beginning of the first to the end of the last. It told us in the problem that this blue force was going to remain 46 newtons because in the picture, the way the astronauts are oriented, that's going to be a right angle. Now, unlike the last problem, we can't just assume this to be 45 because these two sides are not equal to one another. It's some angle theta, but we don't know what it is. We need to calculate it. So, first thing we need to do, find the hypotenuse of this right triangle. Do that now. When I plug that into my calculator, I get 74 newtons, but remember that's just the magnitude. We also need to find the direction. This is a right angle, a right triangle, so we can use our right angle trig to find the angle. Remember back in chapter 4, if we want to find the angle theta, tangent of opposite, or inverse tangent of opposite over adjacent. In this case, our opposite side is 46. Our adjacent side is 58. Make sure you're in degrees, or you're going to get your angle theta in radians. But figure out what that angle theta is. And I got 38 degrees when I did that. So, taking this information from finding the net force, or the vector sum of force 1 plus force 2, putting those two together, what was that number again? 74 newtons. Now in this case, I'm not going to include the direction at this point in time because that's really going to be important more when we're determining the acceleration of that object, right? So 74 equals 940 kilograms times A. And when we do that, That's what I get for the value of the acceleration, or the magnitude of the acceleration. But, like we discussed before in the previous problem, the acceleration is going to occur in the same direction that the net force is acting. So, if the net force is acting at 38 degrees above the positive x-axis, the acceleration will also occur at 38 degrees above positive x-axis. Another application of Newton's second law, right, using forces that aren't on the same axis, but still go combine together to determine the acceleration of the object. The next example that I wanted to do, I'm not going to necessarily, I'll probably run the whole way through. This is actually from your homework assignment for tonight. It's from the end of chapter 5 in your book, so let me get there real quick. Stand by. Getting there. Probably should have had this ready to go already. I apologize. But why should this be any different than, we're doing so? And of course, it's on 2 separate pages, so I need to grab this. Alright. On page 182, number 87, that then continues on to page 183, just to make it less convenient for me. All right. Stand by. I suppose I probably could have just paused the recording while I did this, but it's a little late for that now. Whew. All right. So this is page 182, question number 87. So it says, 2 astronauts use their jetpacks, common theme today, to push a satellite in deep space. One astronaut exerts a force of 45 newtons in the positive x direction. The second astronaut exerts a force of 68 newtons at an angle that is 55 degrees above the positive x-axis. So, part A says use a ruler and a protractor to determine the approximate direction and magnitude of the net force acting on the satellite. Boo to that. We're not using a ruler and protractor. We have another way to do that, right? Actually, I should do this. We're not going to use a ruler and protractor, but we are going to determine not the approximate direction, but the direction and the magnitude of the net force acting on the satellite. So, part A wants to know the net force. 2 things that we know here. One astronaut exerts a force of 45 newtons in a positive x direction. The second astronaut exerts a force of 68 newtons at an angle that is 55 degrees above the positive x-axis. So I'm going to give 68 newtons and 55 degrees. All right, to find the net force, right? Finding the resultant vector. So I'm going to start this problem with a coordinate system. Okay. Even though I haven't drawn the satellite, this problem or this example works best if we start the middle of the satellite at the origin. And then, like I said, drawing free body diagrams are usually most effective if we draw all the forces starting from the middle and pushing outward. So, force 1, right, 45 newtons along the positive x direction. So something like that. And then it says force 2, 68 newtons, 55 degrees above the positive x-axis. So that would look something like this, right? Notice, blue's longer than red because F2 is greater than F1. The net force is the vector sum, right? Sigma F is equal to F1 plus F2, right? But both being vectors, we can't just add the magnitudes together. We have to find the resultant vector. Just like we did in the previous problem. These two vectors are not lined up properly to find the resultant. So I'm going to take F2 and move it to the end of F1 and then draw in the resultant vector from the beginning of the first to the end of the last. We know that this is 45 because they gave that to us in the problem. And we know that the blue one is 68, but it's not perpendicular to red. We've encountered this situation before. Even though we have two vectors that are not perpendicular to one another, this vector, vector 2, has components. It's got an x component. Sorry, hold on. It's got an x component, and it's got a y component. It told us that this was 55 degrees, and that this was 68 newtons. We can use our trig functions to find the two component vectors of that force 2. Do that now. So that's what I got for the two components of that triangle. Remember though, finding component vectors, the component vectors are equivalent of the vector itself. So finding the two component vectors is the equivalent of removing that from the drawing, along with 68 and 55, and replacing it with those two vectors. Just like we did before, now, knowing that the x component of vector 2 and the y component of vector 2 are perpendicular to one another, now we have a right triangle. And we can find the hypotenuse of that right triangle by doing Pythagorean theorem, keeping in mind that this whole side is actually the sum of these two. They're both on the same axis, so we don't have to do any vector addition there. We just have to add those two together, right? So, doing that, gives us 87 along the x-axis, and now we can use Pythagorean theorem to find that hypotenuse. Do that now. And that's what I got for the magnitude of that resultant vector. Now, in reality, to find the net force, we would have to find that direction as well. It says in the problem, using the ruler and the protractor, determine the direction and the magnitude, but I'm just going to get rid of direction. Okay? All right. Then, just to finish this problem off, not what I wanted to do. Oh well. All right, it says, if the satellite has an acceleration of magnitude 0.12 meters per second, what is its mass? So part B is asking us, I'll use purple again. Part B, sorry, no purple. Part B, what is its mass? But it gave us that the acceleration has a magnitude of 0.12 meters per second squared. We learned from the first part of this section, or the first part of this chapter, that Newton's second law says net force is equal to mass times acceleration. In part 1, we already figured out what the net force was. So we'll plug this in here. I know that's not correct sig digs, but I'm going to go with it, because if we round to sig digs, it's going to be a little bit weird on the answer. We're trying to solve for mass, and they told us that the acceleration was 0.12 meters per second squared. So then we can solve for the mass. That's what my calculator gave me. 2 sig digs here, 2 sig digs here, 2 sig digs here. I will round that to 860 kilograms. Conceptually, we have not done anything different today. We've applied Newton's second law, net force equals mass times acceleration. We have solved for resultant vectors, same thing we did back in chapter 4. So we haven't introduced any new concepts. We've just been applying them in a different way. So, going back to the calendar for tonight, right? Homework assignment that shows, right? Problems from the end of chapter 5. I've already done one of them for you, number 87. Some of them are a little bit simpler, like the ones that we did at the beginning of class. The ones like 88 and 118, definitely more challenging. If you're feeling sassy, go for it. Notice also too, right? I have already attached the answers to that homework assignment, so they are there waiting for you if you want to check it out. Okay? Tomorrow, we come back, we will talk about gravity, weight, normal force, and apparent weight, which will get us further into section 5.2, applying Newton's second law in another different situation. I'll see you guys tomorrow. Have a good evening.